Hello again, this is Masa-aki Haga. I've talked about coordination chemistry and electrochemistry already 8 times. Today, in my 9th seminar, I'll discuss electrochemistry of absorbed species on an electrode. Today's topics I'll discuss is listed here. The first, how different the cyclic voltammogram shapes when chemical species absorbed on the electrode. Second, electrochemistry of self-assembled monolayers, often called SAM as short. I pick up several examples from recent research papers. Third, I will discuss what kind of molecular design is required to immobilize the chemical species onto the surface. Here is a book, entitled Supramolecular Chemistry at the Surface. This book is worth reading to understand the surface structures and functions of molecules on the surface. This book is focused particularly on STM and FM method. The redox reaction at the electrode we have discussed so far focus on the electron transfer between an electrode and chemical species dissolved in solution. That is the homogeneous system. In this case, the mass transport of chemical species onto the electrode is involved, and therefore we can deal with a fixed diffusion theory. On the other hand, when chemical species are absorbed on the electrode, there is no need for diffusion of substrate to the electrode surface. Therefore, theoretical handling of current potential curve becomes easier. The third, in the case of redox in active molecules such as simple long alkyl chain group is covered with the electrode, the absorbed layer acts as the electron transport blocking layers. This scheme summarizes the electron transfer event on the self-assembled monolayer film on the gold electrode. The SAM film contains both simple alkyl thiol groups, and the other is redox-active MM+ functional groups attached on the top. There are different electron transfer pathways possible. Depending on the thickness of alkyl chains, the electron transfer blocking or tunneling are considered both redox species from the solution or redox-active SAM with anchoring group. When the anchoring group becomes longer chain lengths, the electron transfer becomes slower. This figure shows the effect of thickness of alkyl thiol on gold surface on CV shapes. For the redox response of ferrocyanide in potassium chloride solution, no CV response was observed on the gold electrode covered with hydroxyhexadecyl C16 chain, but in the case of hexyl C6 thiol on gold electrode, the broad CV response indicates electron transfer tunneling takes place. Here summarize the CP response at the electrode in solution species or absorbed species. For the electrode reaction of chemical species dissolved in solution, The CV for the reversible system gives the anodic and cathodic peak separated by about 60 millivolt due to the diffusion of species in the electrode surface, as shown in left-hand side. On the other hand, chemical species absorbed on the electrode surface give the CV that is ideal vertical symmetric with zero potential separation between the anodic and cathodic peak, since there is no diffusion on the species. Now, we should consider the relationship between the applied voltage and current as the stoichiometric relationship between the oxide O ADS and RADS absorbed on the electrode when the potential is applied. In other words, the amount of oxidized and reduced species coverage on the electrode surface correspond to the concentration ratios in the Lorentzian equation. So the concentration ratios of oxidized and reduced species changed with applied voltage. In these equations, the time variation of the concentrations change gave the current values, as shown in this equation. For the adsorbed species, the peak current value obtained is proportional to a linear functions of the coverage and the scan rate. The actual CV shape is shown when the redox active complex is absorbed on the electrode. The charging current component is seen over the entire potential range because background current is not subtracted. The separation between the anodic and cathodic peak is small and close to that of the ideal systems. The peak-wise delta EP half at 1/2 of the peak current is 96 millivolt for a 1-electron systems. The peak current value is proportional to the first order of the scan rate. As shown in the inset of the plot, plotting the scan rate on the horizontal axis and the peak current on the vertical axis yield a straight line passing through the origins. Since the CV current for chemical species in solution depends on the square root of the scan rate, it is important to make this plot when determining whether a chemical species absorbed on the electrode. The area of this gray portion of the CV peak by scanning the potential corresponds to the total amount of the charge resulting from the electron transfer between the absorbed species and the electrode. So the concentration of absorbed species can be determined from these areas. When the electron transfer rate between the absorbed chemical species and the electrode is slow, the symmetric adsorption waves is deformed asymmetrically, and the peak potential shift towards anode or cathode potential directions. This potential difference can be used to determine the electron transfer rate between the electrode and the chemical species, known as the Labiron method. Before going further, I'll show you how to make the sum film on the gold surface. At first, the molecules with alkyl or other anchoring group is dissolved in solution. and gold substrate or other substrate is immersed into these solutions and wait for a certain time. In the case of thiols, 1 or 3 hours are enough to immobilize the molecules on the electrode. The modified electrode is removed from the solution and rinsed well with water and the other solvent and measured. The densely packed monolayer film is obtained. Here is the STM image. Now I'd like to present some papers on molecular self-assembled films as an example. The first is the electrochemical study of ferrocene sound film with tripod thiol anchor immobilized on gold 111 surface. Here, reversible waves are seen at 0.24 volt in dichromethane solution. Upon immobilized on the gold surface, the oxidation potential shifted towards anodic directions with a peak half-width of 93 mV, close to the theoretical value. A linear relationship between peak current and scale rate was observed, indicating the characteristic of adsorption waves. The charge value also indicates that the molecules are densely packed on the surface. In molecular sum film on surface, it is theoretically predicted when there are intermolecular interaction present, the electrochemical response of the CV shape will be different. In other words, previous CV shape on absorbed species are based on Langmuir isotherm adsorption model, which does not involve intermolecular interaction in the absorption process. However, when the intermolecular interaction becomes involved in the redox behavior, the Fromkin model must be considered. When intermolecular interactions are present, an interaction energy term must be added to the represent the coverage of oxidized and reduced species, and the equation takes in this form. In other words, interaction between molecules in different oxidation states, such as oxidized, reduced, oxidized species, and reduced species on the surface needed to be considered. In the two-dimensional plane, various combinations such as those shown here are possible and require a statistical mechanical approach. If the interaction is an attraction, the CV peak will be steep. If it is a repulsion, the peak will be broadened, sometime separating into two peaks. In the previous slide, Lavinon theory predicts the CV peak will be steeper in the presence of intermolecular interactions. I show you two examples of some film of several redox-active organic molecules. First is the nitroxy radical sum films on the gold surface. For oxidation of nitroxy radicals, dilution of the surface sum film with simple alkyl chain was found to decreasing the peak current and increasing the peak half-width. The direction of the peak shift upon dilution shift in the opposite direction of each other's when the solvent are dichromycin and acetonitrile. Furthermore, the Cb peak is sharper in dichromycin solvent than in acetonitrile. These changes are contrary to the expectation, since the oxidation of nitroxy radical produces a positive charge, thus strengthening the intermolecular repulsions. However, at the electrode surface, ion pair formation and sorbation change in the electrode double layers that counteract intermolecular repulsion may play important roles. Tetrathiourbaline, abbreviated TTF, is known to form pi-stacking structures as organic conductors, and tetrathiourbaline itself shows this two-step one-electron oxidation reaction to form monocation and then dication form. Upon the TTF arcucycle was self-assembled on gold electrode surface, two oxidation peaks with very different peak half-lives are observed. This Cb indicates that both values of A that indicate intermolecular interactions are due to the attractive interactions, especially in the presence of bication, which gives sharp peaks due to the presence of strong attractive interaction between the pi-stacking structures. In mixed sum film of ferrocene arcucycle and various lengths of arcucycle, the potential shifts more positively when the head ferrocene is buried in the arcuate chain. This may be due to the simultaneous effect of potential gradient and sorbation in the double layers on arcuate groups. The acid-base chemistry on some surface is important to control the functionality on the solid surface. Therefore, some film with a carboxy group as the head group was studied to determine the pK values. The some with carboxy group on gold or silver electrode do not have a redox active group, but interestingly, a peak current is observed when the Cb is measured by scanning the potential at different pH, as shown in this slide. This current potential response is attributed to a non-Faraday current. The pK of the acid or base fixed on the electrode surface is different from the value in solution. The ratio of protonated to deprotonated carboxylate form of the carboxylic acid at the surface is reported to be related to its interfacial potentials, pK and pH, by this equation. Further, the current flowing through the interface can be divided into a pure capacitive current and a protonation-deprotonation current that is directly related to the rate of change of some protonation or deprotonations. The pKa on some surface, in this case, is 8.9, which is 4 units higher than the value in aqueous solution of carboxylate group. As shown previously, it is important to understand how potential and electrolyte effect interface proton transfer at the electrode surface. Here again, the proton equilibrium at the gold surface of mixed for mercaptobenzoic acid and for mercaptobenzonitrile self-assembled monolayers was studied using in situ surface enhanced infrared absorption spectroscopy, (CIRAS). In this case, no peak was observed from the CV of the electrochemistry. Instead, by using CIRAS, we can monitor the protonation by tracking change in absorption of carboxylic acid or carboxylate at the same time, measuring the IR's absorption change at different potentials. The deuterium substitution protonated at 1700 Kaisers and deprotonated at 1400 per centimeters change in opposite directions as shown here. The pK can be estimated from this change. The interfacial potential gradient can be observed by potential dependence of CN vibration using 4-mercaptobenzonitrile, a reporter of the vibrational Stark effect. From this potential gradient, it is found that the change in the value of the applied potentials by APP is only required to change the value of phi exponential by 10%, and that the remaining 9% of the potential drop is due to the potential drop inside the sum. In this example, the combination with spectroscopy measurement would be very effective. Here is another example of ferrocentile sum by combination of XPS for surface monitoring. Ion pair formation in the oxidation reaction of ferrocene on gold surface has been reported from change in CV shapes or capacitance. In these studies, the relationship between the presence of atoms and the applied potentials was directly investigated from XPS measurement in liquid at the electrode surface. The CV of sum is shown here with different anion supporting electrolyte TFSI, VF6, and CL4. The CV significantly changed by not only the potential but also the shapes. The XPS signals of atoms near the electrode surface at 0 volt and 0.6 volt shown the ferrocene cation due to the oxidation. This is due to the strong anion binding to the sum, causing ion pair formation at electrode surface. And this scheme will be proved by measuring directly by XPS measurements. Electrode reaction of chemical species in solution accompanied by the adsorption of reactant or product onto the electrode will affect the shape of the CV. When the reaction product is strongly adsorbed, a prep peak is observed as shown here. If the absorption is weak, an increase in the cathodic peak current is observed. If the reactant absorbed, a positive peak is observed. In the case of weak adsorption, the oxidation peak current increased. I show one example of ruthenium bis bendoimidazole pyridine compound with longer alkyl chain than cations, abbreviated ruthenium DIPOD. The chemical structure is shown here. In acetonitrile solution with tetrabutyl ammonium hexafluoride, the CV shows 1 reversible oxidation waves, or X1, and 2 reversible reduction waves, RD1 and RD2, with desorption sharp peaks. For the oxidation peak, when changing the scan rate, the anodic and cathodic peak current is linearly dependent on the square root of the scan rate, which indicates the redox process is diffusion control process. From CV, we can determine the halfway potential of the ruthenium complex, as shown here. I have to touch on the under-potential deposition of hydrogen or metal atoms on the electrode. As shown here, the polycrystalline platinum electrode in 0.5 molar sulfuric acid. When the potential was received to the cathodic potential directions, 2 peaks for hydrogen adsorption and desorption were observed in the CV. For the positive potential region, broad peak due to the formation of platinum oxide observed. Since the electricity of this hydrogen absorption waves is known to be 210 microcoulombs per centimeters squared, the surface area of the electrode surface can be determined from these values. While the CV of polycrystalline platinum electrode was shown previously, it was recently reported that single crystal surface of platinum can be produced relatively easily by heating a platinum wire in a hydrogen-oxygen frame and then cooling it, and hydrogen absorption on a single crystal surface is now being studied. This is also related to the fact that much research is being conducted to understand hydrogen electrode side of the fuel cell. Here is the atomic structures of the 100 and 110 and 111 crystal plane of platinum. The CV in 0.5 molar sulfuric acid for each of these planes are shown in this right-hand side, and the potential of the sharp peak of hydrogen adsorption differ greatly depending on the crystal plane. It can be seen that the 2 hydrogen reductive oxidative desorption wave at the polycrystalline platinum electrode were from the crystal phase 100 and 110 plane, respectively. Now, when molecules are immobilized on the electrode surface, it is important to select functional groups that allow the molecules to bind to the electrode. The electrode materials and organic functional group are listed here. various combinations are possible. For example, thiol group immobilize strongly to the gold surface. As we can already mention, isocyanide groups absorbed strongly to the platinum surface. On the other hand, carboxylic acid or phosphonic acid group are strongly attached to oxide electrode, silicon titanium oxide (AITO) surface. In these combinations, the HSAV rule, hard and soft acid-base principle, comes into play. This means the soft thiol group are strongly attached to soft gold surface, but not to hard acid metal oxide surface. Pyrene group can also used to anchor non-covalently and reversibly absorbed to carbon surface such as graphene or carbon nanotubes. The orientation of molecules on the surface is also important for further functionalities. In order to control the orientation of molecules, it is important to introduce multipod anchor group in terms of electron transfer to and from the electrode. The partial structures of tetrapod phosphine acid has been synthesized in a group, is shown in here. In dye-sensitive solar with ruthenium complex absorbed on titanium oxide, carboxyl group or phosphonic acid group are introduced on the ligand of the ruthenium complex and fixed on the titanium oxide. It is known that the photoelectron injection efficiency depends on the position and number of anchor groups. Here is a CV of mononuclear and dinuclear ruthenium complex with tetrapod phosphonate group immobilized as self-assembled film on ITO surface. The peak current for dinuclear complex is 4 times larger than that to mononuclear complex, since dinuclear complex shows the 2 electron oxidations. The dinuclear complex could be absorbed perpendicular or parallel orientation to the electrode surface with respect to the axis connecting ruthenium, but we concluded that they are oriented perpendicularly in this way, since both of footprint are the same based on comparison with the surface coverage with the mononuclear complex. In order to functionalize the carbon surface, we used redox-active ruthenium complex with pyrene anchors, which is act as a non-covalent interaction with carbon surface. Here is the example of complex 1 and complex 2, which has the pyrene group on the peripheral group, and sometimes we can synthesize pyrene and phosphonate as the Eunice type, the interaction complex. Here's one example of the ruthenium complex with 4 pyrene groups on HOPZs. You can see that the symmetric absorbed CV waves for ruthenium-2,3 couple was observed, and the peak current is linear relationship of the scan rate. Ruthenium complex with firing group is interlocked non-covalently fashions. Therefore, the complex is dissolved at a certain time, and here is the temporal desorption profile versus the time, which is monitored by CV current. And as you can see, the number of the powering group increased, the desorption rate becoming slower. Here is a summary of today's talk. Today, I focus on the electrochemistry of adsorbed species. The CV shape of absorbed species discussed from the Langmuir isomer model, non-interactions, and Fromkin isomer models, intermolecular interaction present. Several examples for redox-active SAM films with ferrocyan, nitroxy radical, and TTF function groups are shown. And the potential deposition of platinum electrode is also discussed from the viewpoint of platinum-hydrogen adsorption. Selective adsorption on the electrode by anchor group play an important role for surface modification and chemical functionalization on the surface. Here the reference for the reference, and thank you for listening.
Thank you, Professor Haga. If you have any question regarding to the lecture, you can contact us. The next webinar we are planning to schedule for April. The detail will be updated in the beginning of next month in the ALS website. For today, thank you and have a nice week.